Hello and welcome to the Quality Excellence channel. I'm Mayank Agarwal, and today we're diving into something that might sound a bit intimidating at first, but trust me, it's incredibly powerful. Chapter 21, Hypothesis Testing. You're probably thinking, why should I care about hypothesis testing? Well, it's the secret weapon that helps us make data-driven decisions instead of just relying on gut feelings or assumptions. It provides a structured approach to validate our ideas. So, are you ready to unlock the mysteries of statistical decision-making? Let's get started on this journey. Imagine you're a detective trying to solve a mystery. You have a hunch, a theory, but you need evidence to prove it beyond any reasonable doubt. That's essentially what hypothesis testing is all about in the world of statistics and Six Sigma. It's a method that allows us to make educated guesses about a population based on sample data, and then rigorously test whether those guesses hold up under scrutiny. Hypothesis testing isn't just for statisticians or scientists. It's a tool that's used every day in business, healthcare, and even social sciences. In Six Sigma, we use it to validate whether a change we've made to a process has actually resulted in a significant improvement. It's like having a mathematical lie detector that tells us whether our efforts are making a real difference or if we're just seeing random fluctuations. This ensures that improvements are statistically significant and not just due to chance. Now let's break this down into two key players in the hypothesis testing game: the null hypothesis and the alternative hypothesis. These are the foundational concepts upon which our decisions will be based. Think of the null hypothesis, often symbolized as H0, as the boring status quo assumption. It's the default position, essentially saying, nothing interesting is happening here, move along. It represents the absence of an effect or a difference. For example, if we've made a change to reduce defects in a manufacturing process, the null hypothesis would be, there's no difference in the defect rate before and after our change. It assumes our efforts have had no impact. On the flip side, we have the alternative hypothesis H1, which is what we're actually trying to prove. It's the exciting newcomer challenging the status quo, suggesting that our change indeed have an effect. So how do we decide which hypothesis wins this statistical showdown? This is where p-values and alpha levels come into play, acting as our judges in this critical decision-making process. The p-value is like a measure of how surprised we should be by our data if the null hypothesis were true. It quantifies the probability of observing our results, or something more extreme, if there truly is no effect. A small p-value, usually less than 0.05, is like statistics yelling, "Whoa, this is incredibly unlikely to happen by chance." When we see a p-value this small, it provides strong evidence against the null hypothesis, leading us to reject it and accept the alternative. Before we even look at our data, we need to decide beforehand how surprised we need to be to reject the null hypothesis. This is where alpha comes in. It's the significance level, the threshold we set, commonly at 0.05, which means we're willing to be wrong 5% of the time. In other words, we accept a 5% risk of incorrectly rejecting the null hypothesis. If our p-value is less than alpha, we reject the null hypothesis. It's like setting the bar for how much evidence we need before we're willing to say, okay, I'm convinced something real is happening here, and that the observed effect is not just due to random variation. Now you might be thinking, this sounds foolproof. We have p-values and alpha levels, what could go wrong? But hold on, because even with all this mathematical rigor, we can still make mistakes. Statistical analysis isn't perfect and errors can creep in. There are two types of errors we need to watch out for, each with its own consequences. Type 1 error is when we reject the null hypothesis when it's actually true. It's like convicting an innocent person. We're saying there's a significant effect when there really isn't one. Type 2 error is the opposite. It's when we fail to reject the null hypothesis when it's actually false. This is like letting a guilty person go free. We're saying there's no significant effect when there really is one, when in reality there is. Let's walk through the steps of hypothesis testing. First, we state our hypotheses, the null and alternative. The null hypothesis is essentially the status quo, what we're trying to disprove. The alternative hypothesis is what we suspect might be true. Then, we set our significance level, alpha. This is the threshold for determining statistical significance. Next comes the fun part, collecting data. This is where proper sampling methods are crucial. You wouldn't judge a whole pizza by tasting just the crust, right? Same idea here. Your sample needs to represent the whole population. A biased sample can lead to incorrect conclusions, so be mindful of your sampling technique. Once we have our data, we run the test. This is where software like Minitab, Excel, or online calculators come in handy. They crunch the numbers and give us that all-important p-value. Then comes the moment of truth, analyzing the results. Now, here's where things can get a bit tricky. There isn't just one type of hypothesis test. There are several, and choosing the right one is crucial. It's like picking the right tool from a toolbox. You wouldn't use a hammer to tighten a screw, would you? Each test is designed for a specific type of data and research question. The most common tests include the t-test for comparing means, the proportion test for comparing proportions, and the chi-square test for categorical data. So how do you choose? It depends on your data and what you're trying to compare. Consider the nature of your variables and the relationship you're investigating. Let's put all this into practice with a real-world example. Say you've implemented a new maintenance process to reduce machine downtime in your factory. You collect downtime data from before and after the change. Since we're comparing the same machines before and after, we'll use a paired t-test. This test is specifically designed for comparing related samples. Our null hypothesis is that there's no difference in downtime, and our alternative is that downtime has decreased. We're hoping our new process has made a positive impact. We run the test and get a p-value of 0.02. Remember our alpha of 0.05. Since 0.02 is less than 0.05, we reject the null hypothesis. This means we have sufficient evidence to support our alternative hypothesis. In plain English, this means our new maintenance process has led to a statistically significant reduction in machine downtime. Cue the celebration. But don't forget to translate this statistical win into business terms. How much money or time are you saving with this reduction? Quantifying the impact helps demonstrate the value of your process improvement. Now let's talk about some common traps people fall into with hypothesis testing. One big one is confusing statistical significance with practical significance. Just because something is statistically significant doesn't always mean it's important or meaningful in the real world. A tiny difference can be statistically significant with a large enough sample size, but it might not matter in practice. Always consider the context and magnitude of the effect. Don't get blinded by p-values alone. Think about whether the observed difference truly makes a difference. We've covered the essentials, but there's a whole world of advanced concepts in hypothesis testing that can take your analysis to the next level. Things like power analysis, which helps you determine the sample size you need to detect an effect if it exists, ensuring your study has a good chance of finding a real difference. Or bootstrapping, a resampling technique that can be incredibly helpful when your data doesn't meet the strict assumptions of traditional tests. And let's not forget Bayesian inference, which flips the script on traditional hypothesis testing, allowing you to incorporate prior beliefs into your analysis. These advanced methods offer powerful tools for tackling complex research questions. And there you have it. We've journeyed through the fascinating world of hypothesis testing. To summarize Chapter 21, hypothesis testing is critical for validating improvements and making data-driven decisions. Always define HEO and H1 clearly, ensuring you know exactly what you're trying to prove or disprove. Use p-values to guide decisions, but remember they're just one piece of the puzzle. Choose the right test based on your data type and the question you're trying to answer. This method ensures your conclusions are backed by solid statistics, not just gut feelings or assumptions. That wraps up Chapter 21, Hypothesis Testing. I'm Mayank Agarwal, and you're learning with the Quality Excellence channel. If this helped you make sense of statistical decision-making, be sure to like, share, and subscribe. Up next is Chapter 22, Sample Size. Until then, stay curious, stay data-driven, and I'll see you in the next video.